let's play that game for the making change example. All right, just as a reminder, we have all these coins and our goal is to make up 92 cents with as few coins as possible, right? So we're going to consider the quarter first. Here we take the quarter, we take the quarter, we take the quarter. Oh, we can't take a quarter because it's too much, right? So we have this algorithm, right? So let's jump into the middle of the computation. Let's say at time t minus 1, the algorithm has committed to these two quarters. That's the first, right? So this is at minus 1 is taking these two quarters. And then the fairy godmother, remember, she's holding some solution, ideally an optimal solution, that's consistent with what the algorithm has done. So the algorithm is taking these quarters, she has these quarters as well, and then, but she has a full solution, and as a full solution, it adds up to 92 cents, right? And then the algorithm at time t commits to another quarter, say this quarter right here, the slightly different green quarter, and we're going to say that this solution is not consistent, just to make, you might say one quarter is the same as another quarter, but just to make this example a little bit more interesting, we're going to say having a different quarter is a different solution. So the fairy godmother no longer is holding a full solution consistent with what the algorithm has done, because the algorithm at time t committed to a different quarter, right? So the prover has to massage this solution, has to massage the solution st minus 1 into solution st, so it's still a valid optimal solution, still just as good, and it's consistent with everything the algorithm has done up to time t. So the obvious change, right? The obvious change is simply for the fairy godmother to drop the extra quarter that she had and to take the quarter that the algorithm took, right? So that's a really minimal change. And you can see that if what she had before was valid and optimal, then what she has now with that small change is going to be just as valid and just as optimal, right? And valid means it still adds up to 92 cents. Optimal means it still has the minimal number of coins. Here, you might notice I turn the less than around because we're trying to minimize the number of coins. And so, oh, I guess here I haven't turned it around yet, but we will have to turn it around because we want the number of coins to be less than or equal to. All right, so let's think about how the prover is going to change her solution, right? So you can think about the prover as being an algorithm where it takes as input the solution the fairy godmother has, and takes as input what the algorithm does next, and it returns the new solution, right? It takes as input st minus 1, it returns st. And so as we're designing this algorithm, we don't know what the input will be. We don't know what the fairy godmother will have, what solution st minus 1 will be. So we have to figure out what the various cases are, right? So what do we know about her solution? If her solution meets the precondition, then it is a full valid solution. So we know it adds up to 92 cents. And if it meets the precondition, we know it's consistent with what the algorithm has done so far. So we know that she has this quarter and this quarter. And so we know about this 50 cents, and we know she has 92 cents. So that means there's 42 cents that she has that we don't really know about until we get her solution, right? So that's 42 cents that's outside of what the algorithm is committed to at time on t minus 1. And if we want to make this general as possible, what do we know about how much she has outside? Well, we know the algorithm just committed to another quarter. So we know that there's at least 25 cents outside of what AT minus one is committed to. And so that we know that the fairy godmother has at least this quarter. All right, so there are lots of different cases. And so let's think about those cases. In order to make sure we understand all, right, we ensure we cover all the cases, let's build a tree of cases, right? So what we're trying to do is what does she has at least 25 cents or 42 cents of coins outside of AT minus one, and we're considering what those cases are, right? So the first sort of branch is two cases. We could say, well, how many quarters does she have outside of AT minus one? And we can consider the case where she has at least one quarter outside of AT minus one, and we can consider the case where she has 0 quarters. And within that, we can branch on, sub cases, right? This case here, case where we have 0 and then sub cases, so we can say how many dimes does she have outside of what the algorithm has done, and maybe she has 0, 1, 2, 3, or more than 3 dimes, right? And then within that we can talk about, well, how many nickels she has, how many pennies she has, right? And for each of these leaves here, we're going to have to prove that in that case everything works out the way we want it to work out, right? Now, let's just look at the cases here. Do we have something? We know in this case we have 0, she has 0 quarters, she has 2 dimes, and we also know that she has at least 25 cents outstanding from outside of AT minus one. So in this case, down here, we know that she must have lots of, or at least one nickel and pennies, right? So these are all our cases. And let's go through the cases one at a time. This circle, this leaf here represents the case where she has at least 1 quarter outside of AT minus one. Here's the case we have right here, right? She has this solution. She has this took this quarter while the algorithm took this quarter. All we have to do is replace what she took with what the algorithm took, right? And that's what we did and what we showed be doing before, right? So that's one case, right? It handles all situations in which she has at least 1 quarter outside, right? So now let's go over to the cases we haven't considered yet, is when she has no quarters, right? So down here is a place where she has no quarters, but she has at least 3 dimes. And if she has at least 3 dimes, we can tell her to drop those dimes and take instead the quarter that the algorithm has, but then it won't add up to 92 cents, right? Because she dropped 30 cents and added in 25 cents. So we'll give her some other nickel, it doesn't matter which, we'll just stick in an extra nickel, and now she will have 92 cents again, right? So that handles the case when we have at least 3 dimes. Let's go over here where she has 2 dimes and maybe at least one, she has at least, I say lots here, but she has only 2 dimes, she has at least 1 nickel, right? So if she has 2 dimes and a nickel, then she can, here, right? Oops, so here we go. She has, did we done this? Oh, yes. Right, we did the 3 dimes. So the 2 dimes, she has 2 dimes and a nickel. Then we tell her to drop the 2 dimes and the nickel and to take the quarter in question, right? And we can do other sort of cases here. If she has 2 dimes and right, if she has one dime, I don't know, these cases looks like we have two dimes, but you know, we got these various cases, right? And you can see in each of these cases we can replace. We replace what she has with we get her to drop 25 cents worth and replace it with the quarter that the algorithm has taken. Now there's one last case I haven't mentioned yet, and I used to have it be the first case, and students got all excited about it, and so I've moved it to being the last case. Is what happens if she happens to have taken the exact same quarter that the algorithm takes? Well, in that case, there's nothing we should need to do. All right, so that kind of handles all of the various cases here. And so now we need to prove that when we make this change, we changed SD minus 1 to ST in these ways, we have to prove that we have what we want. All right, so we have to prove that ST that we had is still valid. Well, how do we do it? We say ST minus 1 was valid and we introduce no new conflicts. What do we mean by that? That the total, you have to go back and read your question on the test and say, what does valid mean? Valid means that it adds up to 92 cents. And we see, yes, indeed, the amount we dropped and the amount we replaced with is all equal. So if it did add up to 92 cents, it still does. Does it extend what the algorithm has done? Well, we made sure we were only talking about changing coins outside of the AT-1 coins. So we didn't mess that up. And we made sure that it committed to the new coin. So it does, ST does extend AT. Now we need to prove that ST is optimal. Well, we don't know that ST minus 1 is optimal, but what we need is that ST is at least as good as ST minus 1, right? And so if ST minus 1 was optimal, then ST will be as well. Now, of course, there are examples here where clearly ST minus 1 wasn't optimal, right? That's why we relax that ST minus 1 doesn't need to be optimal. But at any rate, we still, even if you're promised that ST minus 1 is optimal, you still need to consider these cases because you want to make sure that all the various cases have been considered, right? Now we're trying to minimize the number of coins. So we're going to say the number of coins in our new solution is no more than the number of coins we had before. So you'll see the number of coins always goes down or stays the same, right? All right, so we proved that ST is valid, extends AT, and is at least as good as ST minus 1. And so that gives us our loop invariant, and we've maintained the loop invariant, and we're happy, all right? So that, however, was only case 1. We're going to have a bunch of other cases. So let's start back at the beginning. The algorithm commits to these 3 quarters, and the fairy godmother has an optimal solution consistent with taking those 3 quarters. And then the algorithm, what does it do? It rejects the next quarter, and the prover needs to possibly change ST so that it's consistent with ST minus 1. And is it possible that the fairy godmother took this extra quarter? Well, we'll say it's not possible because we do know that what the fairy godmother has is consistent with these 3 quarters. So she has the 75 cents. And if she took this extra quarter, then she would have too much. And so she must reject this extra quarter as well. So we know that when the algorithm rejects this quarter, what the fairy godmother has is consistent with that. So this is a case that's pretty easy, but still needs to be mentioned on any test. And that maintains the loop invariant. Right, so now there are other cases, right? Maybe the algorithm has committed to these quarters and the solution, fairy godmother has this solution, and then at time t, the algorithm takes the next dime, or takes another nickel, or takes a penny, and we need to consider all of these cases, but they're very similar to the cases we had before. All right. Just, that's the focus, when we're doing loop invariants, we just do these one step at a time sort of way of looking at it, but let's think about the whole process of the algorithm, right? The fairy godmother is always holding some optimal solution that keeps changing. The reason it keeps changing is because the algorithm keeps making more choices, and the prover keeps changing what the fairy godmother has to be consistent with these new choices. And so and as knows more and more about what the fairy godmother is having, until in the end the algorithm has committed to everything, and we know exactly what the fairy godmother is holding. All right, so now if we're going to be doing loop invariants, we need to establish the loop invariant and get the postcondition. So how do we establish the loop invariant? Well, initially the algorithm hasn't made any choices whatsoever, so every solution is consistent with that. So every optimal solution is consistent with that, and so there exists at least one optimal solution consistent with the choices made so far, because the algorithm hasn't made any choices yet. How do we get the postcondition? Well, the exit condition tells us that the algorithm has considered and committed to or rejected every object. So the algorithm is holding a full solution. And if the loop invariant tells us that there exists an optimal solution that's consistent with that full solution, well, then that optimal solution that exists must be what the algorithm is holding, because it's holding a solution. And so the code will return that solution, and we get our postcondition that the algorithm has returned an optimal solution. All right, so just for fun, let's go back and consider. This is just saying that we've completed this problem, and we've done all the loop invariant things, particularly this step of maintaining the loop invariant is changing solutions, and we've proven that the algorithm works. All right. So before we go on, let's consider this funny case again, where we had coins 4, 3, and 1. We're making up 6 cents, right? So we saw that the optimal solution doesn't contain a 4, while the algorithm commits to a 4 first, making a mistake. So let's try to prove that this algorithm works. We start with the algorithm committing to nothing, and the fairy godmother is holding an optimal solution, which is the 2 3s. And then the algorithm commits to the 4 cents, and the job of the prover is to massage the 3 3 solution into an optimal solution, so a solution that has the same 2 coins, but that contains the 4. And you can see that that's just not possible. And the reason it's not possible to prove that the algorithm works is because the algorithm does not work. The way you prove an algorithm does not work is by giving one counterexample like this, where the answer given by the algorithm is not optimal. Right, so how fast are these greedy algorithms? Well, the bottleneck is the n-log-n of sorting the algorithm of the objects in the input. And then once that's done, you can whip quickly through the objects and make decisions about them.